السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. إن شاء الله today we will be finishing CSPs. Last time we started to talk about tree structured CSPs and how efficient we can solve these kind of problems, and then we started to talk about how we can exploit this idea even if the constraint graph is not a tree structured. And the main idea here is to do what we call Cutset conditioning. So Cutset is the set of variables. If we remove these variables from the constraint graph, the graph will turn to be tree structured, which means the graph will not have cycles. And Cutset conditioning is to instantiate all the Cutset variables by values and propagate these values, or the effect of these values, doing something like forward checking within the graph, and then the graph will turn to be tree structured, and we solve it, and we augment that solution with the assignment that we did in Cutset conditioning. Okay. The runtime of this is the following. For the Cutset itself, we might, in the worst case, try all possible values for the Cutset. So we have C variables. We assume that we have C variables for the Cutset. So trying all possible values will take d to the power c times, because d for each one, d to the power c. Then for each we solve it using the algorithm that we saw last time, which takes n squared n d square, but n here is n minus c because we already excluded c variables. Okay, for small values of c, this is very fast, and compared of course with the general algorithm, general solution, which is d to the power n, this is much faster. This slide also we started last time, talking about how we can do Cutset conditioning. So if we have this constraint graph, and of course the Cutset here is just SA, because if we remove SA, then all the links here will be gone. I mean, all the cycles will be gone, and we will have a tree structured CSP. So the first step is to choose a Cutset, then to instantiate the Cutset with all possible values. Okay, then take one of them and propagate the blue value here. For example, in this graph, we propagate the blue here, so to remove the blue from all the domains of the neighboring variables. Then we solve the problem. So now we have tree structure problem. We solve that problem, and then we augment the solution with blue for SA. If we found the solution here, we are done. If not, then we have to try another value for SA, which will be red here, and so on. Okay, so this is the Cutset conditioning idea. Here is a small quiz for you. That's not, of course, the quiz that you are waiting for, but that's a quiz that is related to Cutset. So find me within that constraint graph the smallest Cutset. Any answers? Faisal? Okay, if we remove A and B, we don't have cycles. Let's see. If we remove A only, what will happen? All of these cycles here, so we will get rid of all of these cycles, but these are still there. So if we removed both, then we will just have this boundary nodes, and we will not have any cycles. Type. So A and B now is the smallest Cutset. Thanks, Faisal. If we removed A and B, then we have to condition them. We have to instantiate them. Okay, so we'll have to assign a value to A and assign a value to B, and then we solve the problem as a tree structure problem. How many possible values for A and B depends, of course, on their domains. If we have 3 possible values in each, then we might have 9 pairs if they are not conflicting. But of course, we don't have to try all of them. Maybe we find a solution before we try all of them, then we will be done, and we don't have to go through the other values. So this is so we are done with Cutset conditioning. Any question before we jump into the last topic in CSPs? Any questions? Yes, Hamza? But a node that has the most edges might not be problematic at all, Hamza. Yani something like this. Let me. It's a good question. If I have something like this, for example, let's say that we have so many edges here, and all 2 different nodes, like that. This node has no cycles, right? Although it has so many nodes. So it's not, it might be a greedy strategy if we want, but it might not guarantee that we will remove the cycles. It's better to remove the cycles. So there are algorithms, of course, to see where the cycles are, and then once you define the cycles, maybe the intersection of the cycles will help here. We'll not study this here in this course, but there are there are, of course, algorithms to find cycles. Okay, thank you. Oops, sorry. Sorry, give me a second. Okay, let's move on to the last topic in CSP, which is what we call iterative improvement. Iterative improvement. So what do we mean by iterative improvement or iterative algorithms here? Iterative algorithm here is a special case, or is a different type of search algorithms, which is called local search. So in local search, we typically work with complete states. So all of the search algorithms that we discussed earlier in the course, we start, especially for CSP, of course, we start with unassigned variables, and then we assign one at a time, right? This one is completely different in the sense that we start with complete state. Complete state means we have value for all the variables. Of course, it might be different values, but we have one value for each variable. Of course, this assignment might not be a solution. That's okay. We start from that, and iteratively we improve it by changing one value of a variable until we reach a solution. So that's the idea. So if we have that toy example, a constraint graph that has 2 nodes, we can start with these assignments. Red, of course, this is violating the constraint, but then we can change one value. We can change the value of one variable. So let's say that we choose the second one or the right one, we change it to blue, we are done. Of course, this is a toy example. In larger problems, we will have to go through several iterations until we find a solution. But the main idea here is that we will start with a complete state. So we don't have a fringe, we don't have states that we will explore later. We only consider one state, which is always complete. Of course, it might not be a solution, it might violate some constraints, but then in iterations, we change a variable to a value, and that value, of course, we choose it in a specific way so that we get closer to the goal, or we get closer to the solution. So in doing that, we use what we call operators Okay, so the operators, of course, the type of operators depend on the problem. The operators reassign the values of the variable. So the main algorithm here is to go through this, you can think of it a loop, okay, infinite loop actually, until we find a solution. In that loop, or in every iteration, we do two things. We select a variable and we select a value. So the variable selection is done randomly, selecting any conflicting variable. What do you mean by conflicting variable? A variable that has a violated constraint. And then we select the value with the minimum conflicts. So to choose a value that violates the fewest constraints. So let's see a couple of examples on that. The first example is the for queen. Here the variables are the position within the columns. Okay, so this is now columns, not rows. So initially we start with a random. We can start with a random assignment to variables. So with random variables, of course, with random assignment to the variables, of course, most probably we'll have conflicts. So in this initial state, we have 5 attacks here. So H here, we call it an evaluation function. Okay, that will tell us whether we reached the goal or not. So H here is 5, and we want to reach the goal of H equals 0, of course, with no attacks. So starting from that state, we will select a variable that is conflicting. Of course, here all of them are conflicting. So we choose one of them. We choose the second one randomly. Okay, now for the second one, we choose an assignment for it with the minimum conflicts. So if we for that variable, let me change the pen here. For that variable, we can move it to here or here or here. Here or there, we still have conflicts because it is attacked by others, but here it will not. Okay, so we choose to move it to that position. Now with that position, now we have a new state, but the evaluation value for it is better. Now H is 2, so we are closer to a solution. Now we choose one of the conflicting variables. We happen to choose this one. Okay, now we have 3 possible values. Of course, we choose the one that has the minimum conflicts, which is in this case 0 conflicts, and we put it in that position. Once we do that, we are done. We have a solution. Okay, so in some cases, this will be very efficient, very fast, because we are on the edge always. We don't build up the solution one variable at a time. We have all variables assigned, but we just need to do some tweaks with the variables, some changes to the variables, so that we can get to the solution. So that's the idea of iterative improvement. Let me show you a couple of demos here. So that's 5 queen, and the variables here are rows. So now we have each variable of these has 4 conflicts, so we can just choose one of them, any of them. So in this case, we chose this one. Now we need to move it somewhere. So which position we should move it to? We have to select the value that has least conflicts, least minimum number of conflicts, which will be that position. So we'll move it to that position. Now it has 0 conflicts, and of course we have to update these numbers. Now each one of these has 3 conflicts or 3 attacks. So we choose one of them. We choose this one. Now which position we should move it to? One of these 3. Of course, randomly we'll select one, so we put it here. Okay, so now we have this assignment. Still it is conflicting, by the way. It is still conflicting, so we have to choose one of these 4 variables. Now we choose this one, and sorry, a step before that. Yeah, we chose this one. Now we can put it here, 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 or there. This is 0 conflicts, so we will move it to that position. Now once we move it to that position, this one has 0 attacks now. Okay, and we have 2 remaining. We choose one of them, and choose one of them, so choose this one, we moved it here, and then we move that one here. Okay, so on. We will continue in iterations, selecting a variable, conflicting variable randomly, and then choosing the value that has the minimum conflicts. Another example here with map coloring. I think you love map coloring now. Okay. So with iterative improvement, this is unusual because usually we start with no assignments at all, but with iterative improvement we start with all assignments. So in this case, let's say that we randomly assigned the values to the nodes, the colors to the nodes. Now we have conflicting constraints, of course. So all of these orange highlighted ones are conflicting. We will start to satisfy them. Okay, so we'll choose one of them. Let's say that we'll choose this one, and if you remember, that one was red, so we change it to blue. Okay, now this one is no longer conflicting, and so on. Choose another one. We chose now this one that was green, and before we chose it was, sorry, we chose this one first. Actually, no. Okay, so this one was conflicting with 3 constraints here. If we change it, then this will be gone. So we change it to let's see here, red. Now these are okay, and so on. We'll continue choosing another one, okay, until we find a solution eventually. So this one now is a complete solution. We don't have any conflicting constraints. Question from Yusuf, I think. Wa alaikum salam wa rahmatullahi wa barakatuh. Yes, but in practice it will reach. In practice it is efficient. Okay, we will talk about a set of problems that will be very problematic for this problem, but in many cases it will find a solution. Remember that, and this is also answering Hamza now. Remember that the algorithm will go until it finds a solution. Okay, and every time we are choosing a value that is minimum with minimum conflicts. So it will reach a solution, but it's not guaranteed to reach it very quickly. In practice, it will find a solution, but it will find a solution efficiently, I mean, but it depends a lot on one thing. What is it? Yusuf, do you think can you think with me? What is the factor here that is very important that will affect how fast we can reach a solution? Of course, the complexity of the problem is a factor, yes, and we will talk about it in the next slide. But one factor is how we start. So the initial state is important. If I have a state, if it happened that the initial state has a few number of conflicts, then of course it will be easy. But if it has many, it might not be easy. Okay, so starting state here is a major factor. Plus, of course, the number of constraints and the number of variables, which is kind of the complexity of the problem. Okay, now let's talk about performance, since you already asked about that. With iterative improvement, we can solve almost any n-queens problem in constant time. In many cases, with very high probability. Okay, so it can reach up to maybe 10 million queens in that. So you can imagine how large is this. And the main idea here is that we start with complete assignment. With complete assignment, there are some things that are good, and there are some things that are bad. And with the iterations, we work on the bad ones. Yes, we might make some of the already good worse, some of them, maybe few, but that will be overall faster than building the solution from scratch. To generalize this idea, if we have the ratio between the number of constraints and the number of variables, and we look at the efficiency or the time needed for iterative improvements algorithm to get to a solution, we had, if you look at this curve now, we had two cases, actually we had three cases here. Sorry. The first case is when R is very small. R is very small means the number of variables, we have very large number of variables with very few constraints. Of course, this is an easy problem, right? Once we assign all variables, we can work out the few number of constraints to get them satisfied. So it will take very efficient time. On the other extreme, if R is very large, which means that we have so many constraints but few variables. Once we have few variables, then we will work with few possible values for the variables, okay, overall, and again we can reach a solution quickly. The problematic area is when what we call the critical ratio, okay, the critical ratio, when this ratio is not very small and it's not very big, which means that there is kind of a relation, not a relation. Generally the number of constraints is not much larger than or much bigger than the number of variables, and vice versa. In this case, that will be kind of more problematic to iterative improvements, and it will take more time. Now, how many problems when can we reach this, or how probable we have in our real problems, in our CSP real problems, we will have such situation? Actually, that's not very rare. If this is the whole set of CSP problems, everything is green, which means we are maybe on that extreme or on that extreme. This whole is the hard problems, okay, which is represented by this critical ratio, and most of the real problems are actually here, unfortunately. Okay, so it will take, it won't take trivial time, so it will take time, okay, but with high probability that time will not be so much. Of course, we cannot have a clear bounds here because it depends on so many things. At least it depends on the initial state, okay, but in practice it is really efficient in many cases. Any question before we just summarize everything in CSPs? Any question about this idea of iterative improvements? Okay, Hamza again. It's not very close, but it's not, the ratio is not very small, or it's not very large. Somewhere I cannot say this is one. I cannot say this is one. This is very rough. This is very rough curve. It's not, of course, accurate. Okay. Any other questions? Okay. So in summary, what we studied in CSPs is that CSPs are a special case of search problems. The states usually are partial assignments when we build up the solution one variable at a time, but of course we towards the end we studied this local search idea, which is iterative improvement, which starts from complete states. The basic solution for CSPs is backtracking search. We studied multiple ways of making it more efficient, ordering of variables and values, filtering, in which we studied forward checking and arc consistency, which look ahead in the future before making the next steps or making the next assignment of a variable. And also we exploited the structure. Okay, we looked at how we can solve the tree structured CSPs efficiently, and how we can convert CSP problems into tree structure problems and solve it efficiently also. And finally, we studied the iterative improvements, which is, as I said, often effective in practice. Not all the cases, of course, but in many cases it will be effective. Okay, so this is a new session. So far we started 3 sessions. I think the first one was just an introduction. Then we studied search algorithms, and in the third one we studied constraint satisfaction problems, or CSPs. Now we'll study what we call local search. We started already this lecture talking about iterative improvements, which is a special case of local search in general. So what is local search, or how it is different from tree search? Again, tree search keeps some of the potential solutions on the fringe. Unexplored alternatives will be on the fringe, and we keep getting one of them at a time to try. But in local search, we only take care of or consider one single current state, and we keep improving it until we can't, whether we reach a solution or we cannot reach a better state from what we have. So the state space here is a set of complete configurations, and the new successor function will produce local changes. So again, with this example, if we started with this assignment, then we have 4 next states with local changes. So we can change this to be green or blue, or we can change this to be green or blue, because of course we don't want to violate the constraint here. Generally, this idea of local search is much faster and much more memory efficient, just because we don't have the fringe. We just keep one state and we keep changing it. But it is incomplete and suboptimal, as we will inshallah see later. So in local search, we will study 4 algorithms: hill climbing, simulated annealing, beam search, and genetic algorithms. Of course, not all today. We'll just start today with hill climbing. So what is hill climbing? It's from the name. If you are you are on a hill and trying to get to the top of the hill, okay, maybe there is a reward or something. If it's really at the day and sunny and you see everything around you, maybe that's okay. But if it's not that sunny, it's cloudy, it's dark, you don't see the whole picture, but you just see around yourself, then what you can do is that you touch the surface around you. You want to go up, right? So you touch the surface around you and you see where is the direction when the surface is going up, and you go into that direction. That's simply the idea of hill climbing. So you check the local neighborhood, the local vicinity, and move to or towards the direction that will give you the towards the goal. Okay, thinking that this is of course the global goal, but it might be local goal or the local maximum, as we will see in the next slides. So look at the local vicinity, local neighborhood, and take the direction that is better, that is the best for you at that moment. Of course, that decision might not be the best you can ever get or you can ever do, because it might not get you actually to the top of the hill, but that's why it's called local search. It's good for you only locally, and you hope that this local decision will lead to the best global decision. This idea is also called greedy local search. Again, greedy because you are just looking at, it's like looking at your feet only. Okay, you just look at your local neighborhood. Mustafa, is that a question? Mustafa? we usually check the time complexity, right? And we also look into memory needs. So this is, yes, of course, you need to check how much memory you have. Are you limited in time or not? What is the time complexity of the algorithm that you are trying? These things are the resources that we assume here, of course. Okay. So this is again called greedy local search, and we can now see hill climbing as a diagram. So on the x-axis we have the states. Okay, imagine that we have the states, the different states we can go over, and on the right, on the y-axis we have the objective function. So in hill climbing, let's assume that we want to get the maximum of the objective function given the state that we are in. Okay, so if we look at the relation between the state and the objective function, we can draw it as a curve like that. If you look at that curve, you will find that this point specifically is the maximum, is the point where we can get the best objective value. We call this the global maximum. Okay, we call this the global maximum, this point, because that's the maximum we can get overall. On the other hand, this is called a local maximum. Okay, why is it called the local maximum? Because in the local neighborhood of that state, it is the best, it is the maximum, but it's just the maximum locally. It's not the maximum globally. Okay, so that's why it's called local maximum. Sometimes also we can get something like this. We call it flat local maximum. It's still not the maximum globally. It's local, but it's flat. Flat means that we have multiple states that have the same value, the same objective value. Okay, so it's not just one state. It's a set of states that have the same value. The difference between this and something like that is that this is if you move in the other directions, you will see that you will have less values, but for the shoulder you have less values in one direction or one side and higher values on the other side. So that's called a shoulder. Again, this is local maximum, but this is a bit different from that case. Now, if we start from that state, let's assume that this is the current state. Where should we go? Based on the hill climbing algorithm, we should go to the state that is the best for us now. What is the state that is the best for us? The state that has the best objective value, the best value for the objective function. So moving to the right is better than moving to the left. So we will go to that direction. We'll keep going into that direction until we reach this point. At that point, all the states in my neighborhood have less value of the objective function. So I am the best locally. So the algorithm here will stop. Okay, so that's hill climbing. Let me take this quick quiz, and then I will answer questions if you still have. So let's say that this is another relation between state space and the objective function. If we start from x here, let's say that we are in state x, where will we end up? Any idea? Okay, raise hand please. I want someone to talk to me. Okay, Yusuf? B, why is that? Yes, no, it's not the local maximum. This one is not local maximum, Yusuf, right? Oh, sorry, you said local, sorry. Yes, it is local maximum. Yes, it is local maximum. I thought that you were saying global maximum, sorry. Yes, it is the local maximum. And the reason why is that we go from X, we pick the state that is better for us. So we go to this direction, we will keep going until we reach this point where we will not find any better states. Thanks, Yusuf. What if we started from Y? Any idea? Someone else other than Yusuf? Faisal? Yes, we will go to D for the same reason. Okay, and since this is flat, we will not get better state, so we'll just stuck at D. Now, what if we started from Z? What if we started from Z? Anyone other than Faisal? Type Faisal. Yes, in this case it will be just by chance. It will go to the global maximum E. It will not go to that direction because that's less value. It will always get a higher value and will move. Will keep going until we reach E here. Okay, Hamza, do you still have a question? Quick question, please, because we want to start the quiz. Okay, so the algorithm that we mentioned here is the standard hill climbing. Inshallah, next lecture we will get to what you are saying.